Okay, so let's get started. Today we're going to talk about regularization. And before we dive in, a couple of announcements. So our first exam, our midterm is next week. So I've updated our lecture notes with a couple of exercises. So if you do them, you should be good for the exam. They're going to be very similar. And in terms of logistics, the exam is going to be taken here. I'm going to have to schedule the lab. So you're going to come and access Moodle. And there will be a task there, which is going to last for the entire time of the lecture. Once you're done, you can finish. You don't have to wait until the end. And what else? For those of you who are remote in Florestal, yeah, I'm gonna assign a place there for you too. I'm gonna keep you posted with where exactly it's gonna be there. And other than that, I think that's pretty much it. And I think last Friday I put up the project proposal on our website. So there's the guidelines for you to how to submit your project proposal. It's going to be a PDF with a max of 2 pages. Please follow the format that I put there. I'm going to use the NeurIPS paper template. It's nice for you to get used to it. And pretty much you're going to have to find a paper. And I put some examples there. If you haven't seen it, go take a look. And there is also a list of conferences that are top-tier conferences in deep learning and AI that are good places for you to look up if you don't have one problem in mind or if you don't know exactly what to work on for this project. I think it's nice to browse in the last editions of these conferences, maybe take a look at the proceedings of the last 3 years of these conferences, look up for keywords of problems that you like, or maybe look up transformers, or there is going to be plenty of models using transformers there. But obviously, not all of them are going to fit the scope of this project because they might be either too advanced papers, or maybe there's not a public data set involved, then or maybe the code is too tricky and hard for some reason. They have some obscure contribution that is hard to follow. So I want you to start looking at this as soon as possible. And if you are not very comfortable, or if you find a paper that you find it that is a good idea, please let me know and I can take a look and see if it's going to be feasible or not. Because you only have a month to work on this. So pretty much we need a data set right away. We need some sort of like code also to reproduce. It's much easier if you have a GitHub repo, for example, from the authors that you can compare to. So the idea here is you're not only going to rewrite their code. You're going to read the paper and try to reproduce the results from the paper. But if you have the code from the authors, then at least you can compare, because most of the time the paper itself, it's not that the details are not there. They are there, but because we have to write in a very compact format, normally you have very limited amount of pages to write, so everything is just very briefly described. So when you have the code, then you can actually make sure that what they're claiming in the paper is there and you can find it. But even if the code is not trivial, because most of this code is not written for commercial purposes. So they are just experimental code that most of the authors write very quickly, and then it's hard to read the code itself. So even if the code, this task of reproducing a paper is very tricky. And as deep learning researchers, you're going to have to do that eventually. You're going to have to download some code and try to run it. And then if you want to improve on top of that, you have to understand what's going on really well and then you have to be able to change it. But the best way to convince yourself that you know what's going on is by reproducing the code yourself. So then if you write your code and it's working as they promised you would work, then most of the time you're guaranteed that, okay, I understood what's going on. Now I can actually go ahead and tweak that and maybe change or improve the model somehow, okay? So the whole idea of this project is to give you an experience of at least doing that once. So when you have to actually do that in your research, you will be one step ahead already, and hopefully that's going to be easier for you. But okay, I think you can leave questions to the end because we have a lot to talk about today. Just a quick recap. Last time we were talking about neural networks evaluation. So we've discussed data set splitting techniques and how to evaluate regression and classification models. Pretty much we discussed a bunch of metrics, right? So for regression, we've seen MSE, or mean squared error, mean absolute error, root mean squared error, and R squared. And then for classification, we saw the confusion matrix that gives us these 4 metrics, which are accuracy, precision, recall, and F1 score. Okay. Remember that these metrics are useful to report or to decide what model to pick, because depending on what's your goal, one of these metrics are going to be better than others. Okay. And if you're working on a problem that you're not 100% sure what metric would be best to use, maybe just compute all of them and discuss all of them. You know. But obviously there's some metrics that are more common in some fields than others. So what happens in practice a lot as well is once you start working on a field, you're going to get used to the metrics that this field already uses, because it's good to have convention. So people keep the same metrics so they can discuss the results on the same page. Okay, so today we're going to still keep talking about experimentation, or somehow like we're going to talk about evaluation, but we're going to move to this idea of regularization, which is techniques for reducing overfitting. So last time we pretty much discussed a bunch of metrics plus kind of data set splitting techniques, but we didn't talk about how to actually perform experimentation with neural networks. So when you're experimenting with neural networks, normally we start with a set of hyperparameters that are you pick from your experience, and then you kind of play this game of trying to solve underfitting and overfitting, and that's what I want to talk about today. And I'm going to present a couple of regularization techniques, including L1 regularization, L2 regularization, and dropout, and 2 other ones that are somehow simpler. So last time we started the lecture asking this question: how do we choose the hyperparameters of our neural network? In other words, how do we choose the number of hidden layers, the number of hidden units per layer, the activation functions, learning rate? There's a bunch of these hyperparameters that you have to choose once you are training a neural network for solving a problem. So to give you a concrete answer, so basically you have to experiment with different configurations and find the one that best perform on your problem. And when I say best perform, is perform on the validation set, which we also call development set for that reason, because it's the set that you're going to try to optimize for. And that's what the set you're going to use to pick your model, or to decide the final specifications of your model, if you will. So here's the scenarios that normally happen when you're training a neural network. So this table shows each column is a result, and the rows here are either training or validation error. So here are the combinations of things that can happen when you're training a neural network. So you either can get high error on the training set and high error on the validation set. And in that scenario you call underfitting, because you're not even performing well on your training data. Right? And keep in mind that we also call that high bias. We say that our model has high bias. This is a more kind of like old style denomination, but it's still like people still use that. So when you hear the word, oh, this model has high bias, it means it's underfitting. Okay. And the other scenario that is very common as well is when you have low training error, but you have high validation error. And that we call overfitting, or also in this old denomination, high variance. So back in the day, people used to discuss this trade-off of high bias versus high variance in machine learning models. Because essentially what we had in the past was this fight between underfitting and overfitting that people would call this high bias, high variance, or bias and variance trade-off. Because the techniques we had to solve this high bias problem would somehow damage the variance of your model and vice versa. So if you try to solve bias, you would damage variance. And if you try to solve variance, you would damage your bias. So then these words come from that time. I'm not going to use these terms very much in this course, but if you find them in the literature, they mean underfitting and overfitting. Okay? And what we actually want at the end is to have low training error and low validation error. Right? So that's our goal when you're training a model. We don't know exactly how to start yet. So far in the assignments, I have given to you some magical configurations that work, right? So I gave you, these, if you start the learning rate this way. So I didn't actually ask you to change the learning rate and figure out the best way. But that's actually what I had to do to give you that assignment, right? I had to find a good configuration for that data set that would lead you to a nice training performance, right? But I had to do some experimentation. In real life, you'd have to do the same. You won't get magical numbers right from the start, right? Here's a concrete example in the problem that you've been dealing with so far in the assignments, which is the image classification problem between cats and dogs. Right? Here, let's assume we have a balanced data set, which is the case for you in the assignments. And let's also pick a human baseline. And this is very important when you are doing experiments. We need what we call a baseline, which is a method that is our point of comparison. So the only way you can argue something is good or bad is by having a baseline. You can't say, oh, pick a magic number, let's say 99% accuracy is good. Right? If you don't have a baseline, you cannot claim that 99% is good. You need some sort of like, okay, what you are compared to. You need some sort of like comparison level, then you cannot make a claim. Okay, because let's say some problems, getting 99% of accuracy is trivial. So maybe what you want is 99.999. The hard part is actually getting the 0.99999. So maybe the most trivial baseline already gives you 99%. So there is no way you can say, oh, this is good accuracy, even though it looks like a high number, right? The only way to claim that is having a baseline. So here we are picking a human baseline as our baseline. What I mean by a human baseline is asking a human to tag that picture. So if you ask a human to look at that picture and say it's a cat or a dog, you're going to have a prediction accuracy of close to 100%, okay? In average, let's say. So that's our baseline here. Ideally, you would like to get as close to that, right? I'm not saying that humans are the best at this task. In fact, if you ask humans to perform the ImageNet task, which are like classifying 1,000 labels or images of 1,000 classes, they're not close to 100% because the images are very slow, or slow resolution, sorry. So some of them are actually ambiguous and confusing. So you can't tell if it's a plane or a bird flying because it's so far away and the image is small, so and the angle is weird, so it's hard to tell. Okay. But anyways, in many AI or artificial intelligence tests, what we want is to be as good or better than humans. Right? So it's very common to have a human baseline in AI. Anyways, so let's look at the numbers, right? A potential underfitting scenario is what you see in the first column there, which is, we got, and here I'm using accuracy, again, because the data set is balanced, so it's good. So for us, making a mistake on dogs or cats doesn't make any difference, right? It doesn't hurt more to miss a cat than miss a dog in this case. So using accuracy as our evaluation metric makes a lot of sense here. Okay. So here we got 45% accuracy in the training set and 42% on the validation set. And we are in this urgent fit scenario because we are very far from our baseline, right? And so on the second scenario, consider that we have changed our model. Maybe we increased it, we put more layers or something. And then start overfitting to our training data. So we got 99% accuracy on the training data, but 67% accuracy on the validation set. So that's a classic overfitting scenario. So the distance between the accuracy of the training set is very high compared to the validation set. So then we would have to tweak our model again, because what we want here is to maximize the accuracy on the validation set. Right? So we have to go back to our training set, change our model somehow to try to get this 67% a little higher. Right? And we will have to do that until we run out of ideas or we convince ourselves there's not much more to do with this data set because maybe it's small enough or we have tried everything we could and then you stop and report, okay, this is my final result. Okay? Eventually you have to stop. And okay, so ideally what we wanted is something on the last column that would bring our validation accuracy to 94%. Okay? Still, that's lower than the human baseline. But again, maybe in this test is going to be very hard to be better than humans. Because this is so simple, right, for humans, cats and dogs, that most likely the best you can do is get as close to humans. Okay? This is different than, I don't want to enter the discussion, but every single task has their best baseline. So think of, let's say, self-driving cars, right? In self-driving cars, we also have humans as baseline. So if you're making a car that drives by itself, right, you don't want to make, if you make less accidents than humans, you're already good enough, right? You don't have to build a car that never crashes. Ideally, that would be ideal, right? If you could make a car that never crashes, then yeah, that would be great. But if you're building these cars, maybe just being a little bit better than humans already is a really good gain in this case, right? So discussing what is good, like how to actually evaluate results in experiments, really depends on how you set up your baselines. Actually, even if you're writing a paper, picking the right baselines really makes your paper stand out or not, or make your contributions stand out or not in respect to the literature. Okay? For example, sometimes you see a new model and people have compared it only against a subset of models as their baselines. But maybe a new contribution would be just picking this same model and testing in somewhere else because the authors haven't thought of that, or maybe there wasn't space enough in the paper to compare to these other baselines. And you could just, okay, let me pick the same model and try out in different fields or different applications. And maybe then these results will suggest that we need to further explore this model maybe in a different application or something. Okay, here is a recipe for deep learning experimentation. Okay? You can follow this recipe for any project you are starting, and that's how normally people develop deep learning models or neural networks. So you start with initial set of hyperparameters. Let's say you pick there are some standard hyperparameters in the literature. Let's say the alpha or learning rate as like 0.01. This is a pretty common set or configuration of learning rate. Maybe you start your MLP, you're going to pick an MLP with, let's say, 3 hidden layers, and each hidden layer is going to have maybe, or I'm going to set them like this. They're going to have 128 hidden. The first one is going to have 128 units. The next one 64, and the next one 32 or something. Right? And then you have, I'm talking about hidden layers here. Okay, not you're going to have an output layer here and an input layer before. How do you start? It's almost impossible to have a good number to start with, to be honest. What people have in mind when they're setting up their initial hyperparameters is based on previous experience. Maybe you have seen a similar data set before, and you've experimented with that data set, and some numbers worked really well. So, I'm going to try to bring those values to here and then try again. So these numbers really, there's no real computation or calculation or heuristics you could use to start with these numbers, okay? We know some stuff, like we know that, the learning rate, maybe it's best to start with a lower like a lower learning rate value than a higher, because we know that at least we don't run into the issue of maybe diverging from the minimum point. So there is some orientation or guidelines you could use to start with these numbers, but they're not going to give you an exact number. They're going to give you just some better starting point maybe. But anyways, you pick a starting set of hyperparameters. You train your model on your train set, and then you ask, do I have high bias? Or in other words, am I underfitting with this model? If I am, say you are in the yes decision point there, then there's a couple of things you should try. You can make your network bigger. So you can add more layers here. Maybe you can add a 256 here and 512. You can add extra layers to your model and add more hidden units. That's going to make your network bigger. It's going to give it more capacity. So if your problem was underfitting, now you're going to be able to represent a more complicated decision boundary, and hopefully that's going to help you solve the underfitting problem. It's a very common way of dealing with underfitting. And also, maybe you don't do that. Maybe you don't increase your network, but you just train your model for longer. So I forgot to put it here, but you also have the number of epochs, right? As a hyperparameter. Maybe you start this with 1,000, right? But then if you run into underfitting problem, you increase this to 5,000. Okay, so you train your network for longer. That might solve your underfitting problem. If these ideas don't work, maybe you can try a different neural network architecture. We haven't seen other more complicated architectures here, but it's also a way to deal with underfitting. So you're going to stay there in that question of high bias until you don't underfit anymore, until your answer here is no. Okay? And then you're going to try our model now and see if it has high variance, which means, in other words, if it's overfitting. Okay? And if it is overfitting, then we are here in this decision point here. And then there is a couple of things you can try as well. The first and perhaps most, not easy, but maybe successful way, or the better way you can deal with overfitting is just get more data. Okay? So if you have more data, then your model, it's going to be harder for your model to overfit, right? Because the decision boundary itself is going to get more complicated, or the perfect decision boundary, let's say. So getting more data is maybe the first thing you can try, but in real life, that's not very easy sometimes. When you are working in a company or you are just dealing with situations where you can't get more data because it's expensive, then you can try regularization, which is this idea I'm going to focus today. Okay? Or you also can try other neural network architectures, but regularization is it's a technique you can use to solve overfitting without getting more data, so that's very powerful. Okay. So remember that when I say here things things to try here for overfitting, remember that you have to get back to the training set, right? We are always training on the training set. But then now in your next iteration, you can maybe try on one of these things. Maybe add regularization, now train the model again, and then validate it again and see if you have gotten better performance on the validation set. And eventually, so you're going to keep playing this game of training, validation, trying tweaking your model, either increasing it or somehow getting more data or regularizing it. Eventually, you're going to reach to this point of you're going to have a good bias and a good variance. Sorry, you're not going to be underfitting and not going to be overfitting. We call this you're going to have a good fit of the data, and then you just report. If you have a test set, just report your final test set, okay? Because that's going to be what we call a unbiased estimator of your error. These error, most likely, if you are in a large data set, most likely this test error is going to be slightly lower than your validation error, but just slightly, not too much, okay? If your data set comes from the same distribution, and if you are if you have done a good job splitting your data set, okay, then your test performance should be similar, maybe slightly lower, but similar to the validation set. Any questions before we actually start talking about regularization? Okay. So formally, in machine learning, regularization consists of simplifying models with the goal of reducing overfit. There is many different techniques. Okay, L1 and L2 regularization are kind of classic approaches for regularization, and Dropout is a more modern approach that has been kind of invented recently in this deep learning era, and is specific for neural networks. The other ones you can use in different models. But Dropout is specific to neural networks. And there is other simple, I'm calling simple because it's kind of more like tricks than actual techniques, in my opinion. It's early stopping and augmenting the data set. They can also be seen as regularization techniques. So before we start talking about regularization, and I want to start by L1 and L2 regularization. To talk about these two, we need to remember some concepts from linear algebra, and there's this particular one that is important, which is a norm. And in linear algebra, a norm is a function, right, that maps a vector into a real non-negative number. And it has three properties. So the function has to return a value that is non-negative, so that's what the first one there says. It has to be greater or equal than 0. And the norm of the vector x, if x is 0, should be 0 as well. Okay? Second one is the norm of the sum should be less or equal than the sum of the norms. And if you have a scalar alpha, if you have the multiplication of the vector, right? If you scale that vector x by that scalar alpha and take the norm, that should be equal to the norm of that scalar, or the absolute value of that scalar in this case, times the norm of x. Okay? So this is just some formalization. What we probably remember from linear algebra is these norms, which are called LP norms, or just L norms. And they're more common, at least for us that take just maybe one linear algebra course in computer science. So L norms or LP norms are just specifics or special type of norm defined as follows. So LP is equal to, so we denote it that way, is 2 bars x, and then there's that little p at the bottom, which is a number to define the norm itself. Okay, so the general formulation of the LP norm is the sum from I equals to 1 until n, where n is the dimension of the vector. Okay, so if you have a 3D vector, you're going to have 3 terms in that summation. Okay, and then what you're going to sum is the absolute value xy raised to the power of p, and then what you do at the end is you raise the whole entire sum to the power of 1 over p. Okay? And there are 2 of these norms that are particularly common, which are the norm L1 and L2. The L2 is the one that we see the most, and it's called the Euclidean norm, and we also call this, we know this formula as the magnitude or the length of the vector. Right? When you have so you probably remember that if you have a vector x, right, we call this v actually. V, you have the x and y coordinate of that vector, right? And if you want to compute the length of that vector, right, you just do x squared plus y squared and the square of this, right? This is the magnitude or the length of the vector is actually what known as the L2 norm. But you can also compute the L1 norm, which is going to be just x plus y. Okay. So this is just some recap or review of linear algebra. And actually the best way to remember this is to do some exercises. So I want you to help me here. Let's compute the L1 and L2 norms for these 2 vectors. Okay. This is L1, and the formulas are up here. So consider now that you have two weight vectors. So this is the L1 norm. So we have this weight vector, could be a weight vector for a linear or logistic regression, minus 1, 2. If I want to compute the L1 norm for this vector, I can write it this way, is equal to, I'm going to sum each dimension of this vector, but taking the absolute values, right? This is equal to 1 plus 2, which is 3, right? And now let's take the L2 norm. This would be written like this. This would be minus 1 squared plus 2 squared, and the square root of this, which is 1 plus 4, right? Square root of 5. And so here is just one example, right? We could do just to see how this generalizes, right? Do this for the second example there. So now I'm going to compute norm 1. And I'm going to write down the formula here so we can get used to this formula. So this is going to be the sum of y from 1 to n, right? And xy. Remember that here there is a 1 because this is p equals to 1. And here we are raising this to the power of 1 over 1. So this is basically the same as what is on the slide there, right? And x, y. So this would be just, again, summing 10 plus 20, which is 30, okay? And for the L2 norm, you're going to have the sum of I going from 1 to n of xy squared, because p is 2 now, and all of this raised to the power of 1 over 2, which is the square root, is the same of, right, the square root of this. And this is the Euclidean norm, xi over 2. That will be just 10 squared plus 20 squared and the square root of that, okay? And then you can do the math. Anyways, it's useful, I think it's useful to do this once to get familiar with the concepts. I know it's tedious. We normally don't have to keep writing or doing this math by hand, but I wanted to get an understanding of what they're computing. So essentially you have a vector and you're computing a number, right? And these two norms give you different numbers, right? Question?
When you do the L2 norm, you have like the size of the vector. When you do the L1 norm, you have what?
It's this. So here is a plot of the L2 norm for the unit circle. Okay. So here the x vector has norm 1. So for the L2 norm, what you get is this plot on the right-hand side. If you keep changing your vector, but in a way that is a unit vector, right? And when you are in the Euclidean space, or you're calling this a normalized vector, right? It has length 1. So then you get this plot. But if you plot the L1 norm, then you get that square there. Okay. These are just real geometric representations of norms. And finally, before we get to regularization itself, we need to discuss the idea of matrix norms. Those are vector norms. Matrix norms are the same thing, but for matrices. And maybe the easiest way to understand them is just thinking of a matrix as a mn dimensional vector. So if you stretch your matrix, right, and maybe concatenate all the rows of the matrix. Then it becomes a vector. And the way you're going to compute the norm is essentially the same thing. So now you're going to sum every element of the matrix, right? So you're going to go from I, which is M is the number of rows, and N is the number of columns. You're going to just sum all the numbers. So you get a matrix, and that operation returns a number that is non-negative. Okay, so it can never be negative because because the way it's defined, right? And you also have norms 1 and 2 for matrices that have the same formulation, but now you just have to sum over the rows and columns. Okay? And so the norm L1 here is summing, has exactly the same idea, right? It sums over all the elements taking their absolute values, and the L2 here, which is also known as this Frobenius norm, is the same, right? The same as the norm 2 for vectors. You sum all the elements, raising them to the power of 2 or taking the square of them, and then at the end you just take the square root of the whole thing. Question? Okay. So I want to compute these norms for these matrices as well, because this operation is actually performed when you are doing regularization. So we were just computing the norm for this matrix, and it's the same idea. I just want you to get used to this. Again, let's compute the norm 1 for this matrix. This would be just summing 0.1 plus minus 0.05, or actually let's write this completely. So we would have the absolute values of all the elements there computed by row plus 0.02 plus 0.15. And that would be 0.1 plus 0.05 plus 0.02 plus 0.15, which is 0.17, right? Plus 15. Is that right? 32, right? Is this correct? 0.32? Okay. And norm 2 would be similar, but now we are going to raise all the numbers to the power of 2 plus minus 0.05 squared plus 0.02 squared, right? Plus 0.15 squared. This is 0.01 plus 0.025 plus 0.0225, right? Yeah. Okay, we are computer scientists, not mathematicians. So. Yeah, and oh, I forgot, and this is the square root of all of that, right? So. I think I have it here. It should be square root of 0.0354. I have it here. I don't know if that's right. It should be something close to that, maybe. It doesn't really matter. Just saying that, again, there's two ways of computing the norm. And essentially, I think the intuition behind here is that we want to measure, we want to have one value that somehow compacts the whole matrix, right? You can think of the size of the matrix if you want. It doesn't make much sense, right? For vectors, it makes sense to look at the size. When you look at the Euclidean space, then size makes a lot of sense, right? It actually matches to how we think of size in real life. But as we actually just saw here, when you look at the L1 norm, maybe it doesn't fit our own intuition of size in real life, but it's a size metric. Somehow it sums all the numbers and it condenses them in one, right? And that's what we need here. Somehow we need to sum all these numbers and make them just one. Oh, wait, okay, so finally, we needed this definition of L1 and L2 norms to define what is an L1 regularization. So the L1 regularization adds to our loss function. So when you're training your model, what you're going to do is you're going to add the norm 1 of your weight matrices to your loss function. So here, so L of edge is our loss function. It could be a BCE loss, it could be categorical cross entropy loss, it could be our MSE loss. This is your loss. And it's divided by, it's already computed for an entire data set, where M here is the number of examples in the data set. Remember, you're just taking the average loss here. But then we're going to add now this term, and you can think of this term maybe as a penalization. So now we're going to train your model with this incremented loss. And if you add to your loss this type of penalization, we call it a L1 regularization, because it's adding to your loss the L1 norm of your weight matrices W. Okay. And lambda here is another hyperparameter controlling how much you want to regularize. So by definition, that's what regularization is. At least L1 regularization is this idea of penalizing your weight matrices by their norms. Okay? And in linear and logistic regression, we don't have a weight matrix, we have a W vector, right? So in that case, then we use the same norm, but for vectors. Okay. But remember that this is a number, right? This is going to result in a single number that somehow condenses all the information of that weight matrix. And you're going to multiply that number by a hyperparameter lambda and add that to your error. Okay. So remember by definition, right, that the norm 1 is defined by that formula. And I'm claiming this here, and I want you to trust me on that. And we have one exercise for this, if you have time now, because we lost some time. But the L1 regularization, what it does, it makes your weight matrix sparse. It's going to tend to make most of the values of your weight matrices to 0 by doing this. Okay? So think of this for a minute. What I'm claiming here is that if you start, let's think of a simple neural network that has, we've been using this network as an example. Obviously, this is a small network, so most likely it won't overfit, right? But just for the sake of the example here, right, we're going to have two weight matrices here, W1 and W2, right? Let's think of W1 only. This matrix here is, what's the size of this matrix? 2 by 2, right? 1, 1. This is my 2, 1. 1, 2, 2, 2. What I'm claiming there is that if you start your matrix, remember that we told you that we normally, in neural networks, we start the weights with values that are close randomly and close to 0, right? So these values are going to be something like 0.01, 0.2 maybe, 0.005, and 0.1. This could be one initial set for when you start training a network. What L1 regularization is going to do over training, if this is your training steps, is going to turn most of these values to 0. Let's say, and the smaller ones, probably this is going to happen. Maybe this is going to become 0.1 and 0.05 or something. But it's going to turn your matrix into a sparse matrix. And my claim here is that if you train your neural network with L1 regularization, and by essentially what, in terms of implementation, the only thing you have to do is to add this penalization to your loss function. Right? And obviously, hopefully you already thought of this, which is if you change the loss function, your gradients change. Right? So our update rule for gradient descent is going to change a little bit as well to account for regularization. Okay. So if you add this term here, now essentially what you're doing, you're changing your loss function, adding a term for penalization. And you're penalizing by the norm. So in some senses, okay, I'm somehow penalizing my model to have lower values for their weights. So I'm trying to, by adding this, and remember, this is a minimization problem, right? So in gradient descent, I'm trying to minimize this whole thing. So because I'm trying to minimize this whole thing, these numbers, the W matrices here are going to decrease over time.
I'm trying to isolate the important neurons.
I'm trying to cancel out some neurons, right? By bringing this to 0, essentially I'm killing this neuron here, or at least this input of this neuron, right? And that's the intuition. So here is a different regularization, that is L2 regularization. It's the same idea. You're going to add a penalization term to your loss function, but now you're going to penalize by the square of the L2 norm. This part here is the subscript tells that is a L2 norm, and we are squaring that. So it's a value. So essentially what you're doing here, we are canceling that square root. Remember, from the formula of L2 norm, there is a square root of the sum of the squares. So by taking that square, we are removing the square root. And, oh, it's right here actually. So by definition, this term here is this norm here, which is the sum of all the values of the matrix raised to the power of 2. And you take the square root of that. But now we are actually computing the square of the L2 norm. So essentially what we get is this, okay? Is the sum of Aij squared to the power of 2. And here I'm using these notations of NL minus 1 and L because these are actually the notation we use for the number of neurons, right? So here would be the number of neurons on the previous layer and the number of neurons of the current layer. So the idea here is the same. It's a penalization, but now it's a kind of a, I wouldn't say it's a softer penalization. So they're going to decrease, but they're going to become values that are close to 0. Okay? And I didn't draw this, but again, guys, another piece of intuition of regularization is if you look at the activation function, and you can think of sigmoid for this. Think of the sigmoid, not sigmoid, think of the 10H. The 10H has a shape like this. Okay? This is 10H function, or activation function, 10H of Z. Z, Wx plus B, okay? If W is small, right? If it's close to 0, this number is going to be, Z is going to be close to 0, and then you're going to use more of the linear part of the activation function. Okay? So what the regularization is trying to do is by decreasing this weight, or this weight matrices, it's going to focus on the linear part of the activation function. And in other words, it's going to make your model more linear than non-linear, which is the values that are higher for W. So when you are on these parts of the activation function, then you're using the non-linearity, which means you're having more complicated decision boundaries. But if your weights are close to 0, essentially you are combining more linear functions, and at the end this is going to become a linear model. So the smaller the values of W, the closer to a linear model you have. Okay? So it's another way of thinking like this. If you're more visual than mathematical, this is one way of visualizing that. Okay? There was an exercise to do that. I hope we have time, because then we can see the numbers actually. I have it here. It's right here actually. And I think this is an important exercise, so we visualize what's going on with the numbers, and at least you understand exactly how regularization is implemented as well. Because remember this, when we have the basic gradient descent, we had this update rule, right? The W equals 2 W minus alpha, right, dl dW. Here, dl dW, I'm calling this, on the slide, I'm calling this just dW, which is normally we use this, I'm using this on the assignments as well, right? I'm just omitting the dl. When you don't see the upper part of the derivative is the L, is the loss function. Okay? This is how you compute gradient descent without regularization. Regularization. But if you want to compute this with gradient descent, with regularization, since we have changed our loss function, this update rule is going to change a little bit. Now, because the partial derivative here is going to change. And it's going to change for L1 regularization is going to be exactly the same. The dW part remains the same. So this is the partial derivative of L with respect to W. But now there is a second term here, which is going to be lambda over m. And for simplicity, I'm going to just assume there's one example here. So it's just m equals to 1. And sine of W. This comes from the partial derivatives of dl, of the loss function with respect to W. But now we have that modified loss function with L1 regularization. For L2 regularization, the update rule is going to change a little bit differently. But we're going to multiply by the sine of W, where sine is basically this. If I have minus 5, 1, if your matrix W is minus 5, 1, 2, minus 3, the sine of this matrix is minus 1, 1, 1, minus 1. Okay, so you just take the sign of each of the values, element-wise. Okay. So, let me change this and bring this up here. dw plus sigma sine. And I'm going to, on the lecture notes, I'm going to put this derivation there so you at least take a look of why this came to be this way. But we don't have to discuss this here right now. But it's pretty much computing the gradients. So I'm going to do it from my notes here because it's faster. And I still have a lot of things to talk about today. What I wanted to show here is, let's start with those matrices. W, and let's just already have that dw computed. So imagine we already have those gradients computed for us, right? Which means this is the result of the back propagation, right? This dw here. So we just have to do the math, which is this part here. This would be equal to, I'm just copying from the slide, 0.1 minus 0.05, right? 0.02, 0.15. Minus alpha is equal to 0.1. dw is that 0.3 from the slide, 0.2, 0.1 minus 0.4. Okay? Let's assume alpha, oh, this is minus, wait, this is here, there's a parenthesis here. This is alpha. And this is plus 0.1, assuming lambda also equals to 0.1. And the sign of w is just 1 minus 1, 1, 1, right? And this is, okay, so this is the original w, right? Now we're going to multiply the learning rate by this result here. So this would be minus 0.1. Copying here 0.3, 0.2, 0.1, minus 0.4, plus 0.1, minus 0.1, 0.1, 0.1. Okay. Yeah, I'm going to have to erase this and do it on the top again. Here I have minus, I already have the result here, minus 0.04, 0.02, 0.01, minus 0.03. This is going to become 0.06 minus 0.06, 0.00, 0.18. So notice how this value here became 0. Okay? And some of them actually increased, right? So this number here increased because of this minus here, but this is because of the direction of the gradient, right? So for this number, I actually had to nudge it a little bit to the right, right? So I had to increase this number a little bit. Right? This one also, so this decreased as well. This one decreased as well, and this one actually became 0. So obviously, to see this becoming sparse, you would have to run this more, right? But what I wanted to show is that what's going to happen with L1 regularization is that more and more of these weights are going to become zeros, okay? And because we don't have time, I'm going to put these same exercise for you on the lecture notes for the L2 regularization. What is interesting here is that notice how by computing the partial derivatives, we don't get the sign, but we get the weight here. So because of this sign function, we get those ones and minus ones. So the effect of this penalization gets much stronger. But here I have the same matrix W. So here if the weights were initially 0.1, I'm not turning this into 1 and then subtracting. I'm actually doing the regularization more with respect to the original value. So it's going to be a softer decrease. And I have this here for you. I'm going to try to do this a little bit faster now that I've seen some math. Here is the classic gradient descent update rule, WL equals to WL minus alpha DWL. This is, again, what is highlighted there is the partial derivative of the loss function with respect to WL. Okay? Oh, sorry, there's a weird animation. But if you, now this is the effect of L2 regularization. Okay? I'm not doing the math, but I'm doing this more analytically with you. So this is the new update rule. That dW remains the same, plus lambda over m times WL. Remember, in the L1, we had this sign here, but for L2, we don't have that. That's directly the matrix. So if you manipulate the numbers here and distribute them a little bit, what you're going to get is this final situation over here. The new update rule could be rewritten as dW equal to 1 minus alpha lambda over m times dW minus a dW. Okay, so this a dW is from the original update rule, okay? And this WL is also from the update rule. But what's going on here is that this number here is going to be less than 1. Okay? So the effect of this is to decay. See how this matrix here, WL, by being multiplied by this number that is close to 1, but it's like, let's say, if your lambda, this is going to depend on your alpha and your lambda, but what's going to happen is you're going to multiply your original weight matrix by a number, let's say 0.98. So you're going to decay your W matrix a little bit every time. Okay, obviously this is going to be proportional to your lambda and alpha parameters. Okay, so because of this property, this technique is also called weight decay, because it's going to decay your weight matrices over time. So more visually now, so we don't stay only on the math side. Consider this neural network with 4 layers, right? Let's imagine it's overfitting on this 2D problem here, right? You can see this very complicated decision boundary that is capturing the details of these points, green and red, especially here, right? You see that this green is mixed. This green is mixed kind of like more close to the red points in the middle. And the network is actually learning that specific shape of your data distribution. What regularization is going to do, when you add, let's say, L2 regularization, you're going to decay a bunch of neurons or weights in your network. And I'm marking them as more lightly shaded there. What's going to happen is the strength of these inputs here that are decayed, they're going to mean less, or they're going to matter less for predicting the final output. Because now you're multiplying these inputs by a very, very small number, 0.00 something. They're still being accounted for, but very little. So essentially what you're doing is almost like your network has been simplified. Right now, it's not. So it's, again, if you're doing L1 regularization, a bunch of these neurons actually are going to become zeros, then you are essentially killing an entire input. But on L2 regularization, you're not. These are going to be close to 0, but not essentially completely 0. So that's the idea. And now I'm solving overfitting by killing, if you want, some neurons there, or just decreasing the norms of my matrices W. So here's another cool idea that's very similar, but is more mechanic than mathematical. So I don't know, for me, this is just how it looks to me. Like, it looks like Dropout was really invented by computer scientists, and the previous ones were invented by mathematicians, right? Because Dropout is this idea that is similar, but what it does is, the idea is to kill some neurons, but now we're going to add some probability to each of the layers, which is the probability of killing or not a neuron. Okay? And this number here, 0.7, 0.5, 0.5, are probabilities to keep the neurons alive. Okay? And we're going to do that before processing each example in the data set. Or before, so before computing the error, let's say I have a data set with 3 examples. This would be 1, 0, 0, maybe. These are my y's, my ground truth. Right. Before predicting the y hat for each of these examples, I'm going to randomly change my network according to these probabilities. And how I'm going to change? I'm going to randomly kill some neurons and try to do the same prediction. So let's see an example. So imagine this first example here, y1. So this is 1, 2, 3. Imagine a for loop here, right? I first kill the neurons of the first layer, and there is a 7% chance of keeping them. So maybe this one in the middle died. Literally, I just kill it. So here, for the second layer, actually all of them kept alive, same. And by chance, the third layer, these 2 there that are lightly shaded, died. And then I compute, now I do the forward pass for this network, for this new network, which was randomly changed. And then I do it again. Now for the second neuron, for the second example, excuse me, I do the same process again. Now I try to predict this output with another random layout of this network. And I do it again until I process all the examples. So every time I'm predicting an output, I'm changing my network a little bit. Okay. So this works magically, but it does work, and it's one of the most common regularization techniques nowadays. And it works really well on large data sets. So the intuition is pretty simple. Before processing each example, you randomly kill some neurons. And we were discussing here offline that killing a neuron here means multiplying it by 0. Okay, so if you encode, how this is implemented is you generate a mask, which is a matrix that are going to be 1s and 0s. It's going to be randomly a matrix of 1s and 0s. And the neurons that, and this matrix is going to be created according to these probabilities there. Okay? And the number, how you're going to pick the distribution of 1s and 0s is going to depend on that probability that you pick per layer. And it's important to keep per layer because you normally don't want a very low dropout rate on the end of the network, because normally you have less neurons on the end of the network and you have more neurons in the beginning. So the way you normally pick these numbers is they're gonna start low in the first layers and then they're gonna go high in the final layers. But since we won't have an assignment for implementing Dropout, which I think is a good exercise, I'm going to put up a code. I already have this Colab that implements a Dropout in a simple network. I think it's very useful for you to take a look at that. Also for the L1 and L2 regularization, seeing that working in code might give you a better intuition of what's going on, okay? And these techniques, I think both L2 regularization and dropout, they are already implemented in PyTorch, so you can normally just pick the parameter. Like you can just select the dropout rate per layer, and also for L2 regularization, you can pick the lambda when you're training your neural networks. I don't think they have L1 regularization implemented already. By the way, L2 regularization is more common. Okay, guys? It's way more used than L1. So here are two, finally, much more simpler ideas that you can use to solve overfitting. So this is data augmentation, consists of generating more examples by transforming your original examples. So imagine you have images of cats, right? Here's an image, and you could generate new examples by transforming your original data in a meaningful way. So how you can transform, that really depends on your problem. In images, it's very common to apply these transformations like flipping, rotating, right? Maybe you can change the colors a little bit. Maybe you can have a black and white if that makes sense in your problem, right? Maybe that doesn't make sense in your application. But picking the right transformations for you really depends on your problem, okay? And how much you can rotate or how much you can, all these things really might depend on what is the content of the image, what you want to try to capture in that image or not, okay? But for same thing, let's say for images, just to make that point, if you're dealing with handwritten digits, you could have a number 4, right? In this problem, it makes sense to distort your image a little bit, right? Because that is going to give you a different type of digit, but that's going to kind of mimic how people write by hand, right? But that same idea wouldn't probably work for images of cats. You wouldn't want to distort an image of a cat that would make it completely unrealistic, and it wouldn't help your problem, right? So the type of transformation you can apply really depends. But the idea here is that by augmenting your data set, you're making your original data set bigger. So it's going to be harder for your model to overfit, okay? It's very simple, very effective as well. For some other problems, not as easy as to do data augmentation. For example, if you're working with text, it's a little bit harder to do that. And finally, this is a final slide. You have early stopping, which is this idea of, okay, just stop your training earlier. And how do you decide when is early enough? Okay, so what you're going to do is you're going to plot your learning curves. So here is your training set, the learning curve on your training set. And by learning curve, I mean you have on your x-axis the number of epochs, and on your y-axis your loss value. And this is a very well-shaped loss function or learning curve. Not all of them look this beautiful. This is a monotonic curve, so this is probably a convex problem, right? There's no spikes here in the middle. So it's decreasing the entire process. This means that most likely this is a convex optimization problem. But if you plot also, you have to plot also your validation set error. What you're going to see most of the time, and especially if you're overfitting, you're going to get some sort of curve like this, where the validation and training set error, they're going to decrease in the first epochs, but eventually your validation error is going to start to diverge. It's going to try to increase, because that means you are overfitting. You are decreasing your training set error, but at that point, your network started to overfit. Okay? So this is pretty straightforward. You just stop at the epoch that gives you this best validation error. Okay? So this is also pretty intuitive idea for dealing with overfitting, right? And then if you want to claim, if you want to write in a paper, for example, how do you pick this point? You would plot this, or you can show this in a table if you want, but you're going to show here that over time, at some point, your validation error started to get bigger, so you stopped it exactly at that point, and you picked that model, okay? Okay, so that was all it. Next lecture, we're going to talk about advanced optimization algorithms for, or pretty much advanced gradient descent algorithms, okay? Thank you, and sorry for the hiccups.